In the depths of space, approximately 1.2 billion kilometers from the warmth of our sun, there exists a spectacle so magnificent that it has captivated human imagination for over 4 centuries. Saturn, the 6th planet from our star, wears a crown unlike any other in our solar system, a series of luminous rings that encircle its equator in perfect harmony, stretching across hundreds of thousands of kilometers of emptiness, yet containing within them the stories of eons past. When the Italian astronomer Galileo Galilei first turned his primitive telescope towards Saturn in the year 1610, he saw something that puzzled him deeply. Through the imperfect lenses of his early instrument, the rings appeared as mysterious appendages on either side of the planet. He described them as ears or handles, unable to comprehend their true nature. Galileo's confusion would persist for decades, as the limitations of 17th century optics kept the rings' secrets hidden in a blur of magnified light. It was not until 1655 that Dutch astronomer Christian Huygens, using a more powerful telescope of his own design, correctly identified these mysterious features as a flat ring surrounding Saturn but not touching it. Huygens observed that the ring appeared to change its appearance from Earth's perspective as Saturn moved through its nearly 30-year orbit around the Sun. Sometimes the rings seemed wide and prominent. At other times, they became nearly invisible, reduced to a thin line, or vanishing entirely from view. This changing perspective revealed that the rings were extraordinarily thin compared to their vast width, tilted at an angle to Saturn's orbital plane. As the decades passed and telescopes improved, astronomers discovered that what appeared to be a single ring was actually multiple rings, separated by gaps of varying widths. In 1675, Giovanni Cassini identified the largest of these divisions, a gap nearly 4,800 kilometers wide that now bears his name, the Cassini Division. This dark band, separating what we now call the A and B rings, suggested a complexity that earlier observers could never have imagined. The rings themselves seemed to glow with an ethereal light, reflecting the distant sun's rays with remarkable efficiency. This brightness puzzled early astronomers. What could these rings be made of to shine so brilliantly across such vast distances? The answer would not come for centuries, requiring not just better telescopes, but entirely new ways of studying the cosmos. Spectroscopy, which allowed scientists to determine the composition of distant objects by analyzing the light they reflect or emit. By the mid-20th century, scientists had determined that Saturn's rings are composed primarily of water ice, mixed with smaller amounts of rocky material and organic compounds called tholins that give some regions a subtle tan or pinkish hue. The ice particles range dramatically in size, from grains as fine as powdered sugar, smaller than a millimeter across, to chunks as large as mountains, tens of meters in diameter. Each particle follows its own orbit around Saturn, moving in accordance with the same gravitational laws that govern planets around the Sun and moons around their host worlds. The rings extend from approximately 7,000 kilometers above Saturn's cloud tops to more than 80,000 kilometers outward, yet they are astonishingly thin, in most places only about 10 to 30 meters thick, roughly the height of a 10-story building. If you could shrink Saturn's main ring system down to the size of a compact disk, the rings would be proportionally thinner than the disk itself, yet span a much greater width relative to the planet they encircle. This extreme thinness is one of the ring's most remarkable features, a testament to the precision of gravitational dynamics that have shaped and sustained them. As you settle into this journey through time and space, imagine yourself floating in the silence of the cosmos, watching as sunlight catches countless billions of ice particles, each one tumbling slowly in its eternal dance around the pale golden sphere of Saturn. Here, in the stillness of space, a billion-year symphony plays out in ice and dust, a performance that began long ago and will continue until the rings themselves fade into memory. raining down upon the planet they have adorned for countless ages. To understand the rings of Saturn, we must first journey back more than 4.5 billion years, to a time when our solar system was nothing more than a vast cloud of gas and dust drifting through the darkness of the Milky Way galaxy. This nebula, as astronomers call it, was composed primarily of hydrogen and helium, the most abundant elements in the universe, along with traces of heavier elements forged in the hearts of ancient stars that had exploded long before our sun was born. Something disturbed this cloud, perhaps the shock wave from a nearby supernova or the gravitational influence of a passing star. Whatever the cause, the cloud began to collapse under its own gravity, slowly at first, then with increasing speed as its material drew together. The center of this collapsing cloud grew denser and hotter, accumulating more and more mass until the pressure and temperature became so extreme that hydrogen atoms began to fuse into helium, releasing tremendous energy. Our sun had ignited, beginning its long, stable life as a main sequence star. But not all the material fell into the nascent sun. A rotating disk of gas and dust remained, swirling around the young star like water circling a drain. Within this protoplanetary disk, particles began to stick together through gentle collisions, forming larger and larger clumps. Near the sun, where temperatures were high, only rocky materials and metals could remain solid. But farther out, beyond what we now call the frost line, approximately 450 million kilometers from the sun, temperatures were cold enough for water to freeze into ice and for other volatile substances like methane and ammonia to condense. This frost line was crucial for the formation of the giant planets. Beyond it, the building blocks of planets included not just rock and metal, but also vast quantities of ice. This additional material allowed planetary cores to grow much larger in the outer solar system than in the inner regions. When these cores reached approximately 10 times the mass of Earth, their gravity became strong enough to capture and hold onto the hydrogen and helium gas that still filled the protoplanetary disk. Saturn formed in this outer region, approximately 1.4 billion kilometers from the Sun in its current orbit, though some theories suggest it may have formed closer to Jupiter and migrated outward during the solar system's chaotic early years. The planet's core, composed of rock and ice, grew rapidly, and once it reached sufficient mass, it began accumulating the hydrogen and helium that would come to make up most of its bulk. Today, Saturn is the second largest planet in our solar system, with a mass 95 times that of Earth, though its density is so low that it would float in water if an ocean large enough could be found to contain it. As Saturn grew, it spun rapidly, completing a rotation in just over 10.5 hours. A remarkably short day for a planet so massive. This rapid rotation caused the planet to bulge significantly at its equator and flatten at its poles, giving Saturn an oblate shape that is visible even through small telescopes. The planet's equatorial diameter is approximately 120,500 kilometers, while its polar diameter is only about 108,700 kilometers, a difference of nearly 12,000 kilometers, roughly the diameter of Earth itself. The young planet's gravitational field was powerful, pulling in material from the surrounding disk. Some of this material formed Saturn's extensive system of moons, more than 80 of which we have discovered to date, ranging from tiny irregular chunks of rock and ice only a few kilometers across to Titan, a world larger than the planet Mercury, with a thick atmosphere of nitrogen and methane and lakes of liquid hydrocarbons on its surface. But some material never coalesced into moons. Instead, it remained in orbit around Saturn's equator, held in a delicate balance between the planet's gravity trying to pull it inward and the centrifugal force of its own orbital motion pushing it outward. This material would eventually form the magnificent ring system we observe today, though the precise timing and mechanism of the rings' formation remain subjects of ongoing scientific investigation and gentle debate. The early solar system was a violent place. Planetary embryos collided and merged. Asteroids and comets flew on chaotic trajectories, sometimes smashing into planets or their moons. Jupiter's powerful gravity perturbed the orbits of countless objects, sending some crashing into the inner solar system while ejecting others into the distant reaches beyond Neptune's orbit. In this tumultuous environment, Saturn and its nascent ring system slowly took shape, each piece finding its place in the grand architecture of our cosmic neighborhood. As you drift in imagination through this ancient time, picture the young Saturn glowing with residual heat from its formation, its atmosphere churning with storms even more violent than those we observe today, surrounded by a disk of debris that catches the light of the infant sun, already beginning to organize itself into the bands and divisions that would, billions of years hence, inspire wonder in creatures not yet evolved on a small blue world, much closer to the warmth of the star at the center of it all. The question of how Saturn's rings formed has occupied scientists for generations, inspiring theories as varied and complex as the rings themselves. Unlike the question of when the rings formed, which we will explore in the next chapter, the question of how they came into being addresses the physical processes and events that could have created such a magnificent structure around this particular planet. One of the earliest scientific theories about the rings' nature came from the French mathematician Édouard Roche, who in 1848 calculated what is now known as the Roche limit. This is the distance within which a large celestial body, held together only by its own gravity, will be torn apart by the tidal forces from a larger body it is orbiting. For Saturn, this limit lies at approximately 2.44 times the planet's radius, or about 147,000 kilometers from the planet's center. Significantly, Saturn's main rings all lie within this Roche limit, suggesting a connection between this mathematical boundary and the ring's existence. Roche's work led to one of the most enduring theories of ring formation, that the rings are the remnants of a moon or moons that wandered too close to Saturn and were torn apart by tidal forces. Imagine a moon, perhaps 300 to 400 kilometers in diameter, composed primarily of water ice, slowly spiraling inward towards Saturn due to various gravitational interactions. As it crossed the Roche limit, the difference in Saturn's gravitational pull on the near side of the moon versus the far side will become greater than the moon's own gravity holding it together. The moon would begin to stretch, deform, and eventually shatter into countless fragments, each following its own orbit around the planet. These fragments would collide with one another, breaking into smaller and smaller pieces over millions of years. The larger chunks would become the house-sized and mountain-sized particles we observe today, while the smaller debris would form the fine dust that fills the gaps between the rings and gives them their diffuse, hazy appearance in some regions. Over time, these particles would spread out into a flat disk, their orbits aligned with Saturn's equator due to the planet's oblateness and the gravitational effects of its moons. An alternative theory suggests that the rings formed from material that was present in orbit around Saturn during the planet's formation, but never coalesced into a moon because it resided within the Roche limit. In this scenario, the rings are primordial, as old as Saturn itself, composed of the same icy material that formed the planet's outer layers and its many moons. This theory has the appeal of simplicity and aligns with the presence of rings around all four of our solar system's giant planets: Jupiter, Saturn, Uranus, and Neptune, suggesting that ring formation might be a natural consequence of giant planet formation. However, observations and calculations have revealed difficulties with the idea of primordial rings. The rings we see today are remarkably bright and clean. Their ice is relatively pure, with only small amounts of darker, rocky material mixed in. If the rings were billions of years old, they should have accumulated more cosmic debris over time, Micrometeorites constantly bombard the solar system's bodies, and over billions of years, this bombardment would have darkened the rings considerably. The fact that they remain so bright suggests they may be much younger than Saturn itself. A more recent and increasingly favored theory proposes that the rings formed from a relatively recent catastrophic event, perhaps within the last 100 to 400 million years. Ancient by human standards, but young compared to the solar system's 4.5 billion year age. This event could have been a collision between two of Saturn's moons, or the destruction of a single moon by a passing comet or asteroid. Computer simulations have shown that such an event could produce a debris field that would gradually spread into rings resembling what we observe today. The Cassini spacecraft, which orbited Saturn from 2004 until its deliberate plunge into the planet's atmosphere in 2017, provided crucial data supporting a younger age for the rings. By measuring the gravitational pull of the rings during its final orbits, which took it between the planet and the innermost edge of the rings, Cassini determined the rings' mass to be only about 40% of what earlier estimates had suggested, roughly equivalent to half the mass of Saturn's moon Mimas, which is about 400 kilometers in diameter. This lower mass supports scenarios involving the destruction of a single mid-sized moon rather than multiple large moons or primordial material from Saturn's formation. Additionally, Cassini observed a constant rain of ring material falling into Saturn's atmosphere, darkening the planet's upper atmosphere in a phenomenon sometimes called ring rain. By measuring the rate of this infall and extrapolating backward, scientists estimated that the rings could be depleted entirely within 100 to 300 million years. Combined with their brightness and purity, this suggests a system in its relative youth, created by some cosmic accident that shattered a moon and scattered its fragments in a glittering band around the second largest planet in our solar system. As you contemplate these theories, imagine the moment of creation, perhaps a moon, peacefully orbiting Saturn for billions of years, suddenly struck by a comet traveling at tens of kilometers per second. In an instant, the impact vaporizes part of the moon and sends shockwaves through its icy body. Cracks race across its surface, and within hours, the moon breaks apart, its pieces spreading outward in an expanding cloud that will, over millennia, settle into the delicate, ordered structure we call Saturn's rings. For much of the 20th century, astronomers assumed that Saturn's rings were as old as the planet itself, formed 4.5 billion years ago from the same primordial material that coalesced into Saturn and its moons. This assumption seemed reasonable. After all, the rings are such a prominent and defining feature of the planet that it was difficult to imagine Saturn without them, as if the rings had always been part of its identity, like Jupiter's Great Red Spot or Mars's polar ice caps. However, as observational techniques improved and spacecraft visited the Saturn system, evidence began accumulating that challenged this comfortable assumption. The rings' composition, brightness, and dynamics all pointed toward a more complex and surprising story, one in which these magnificent structures might be mere newcomers to the Saturn system, cosmologically speaking. The first hints came from studying the rings' composition. Spectroscopic observations, which allow scientists to determine what materials are present by analyzing the wavelengths of light they reflect or absorb, reveal that the rings are composed of remarkably pure water ice, between 90 and 95% water ice by mass, with only small amounts of rocky silicates and organic compounds. This purity was puzzling because space is not a clean environment. Over billions of years, the constant bombardment by micrometeorites, tiny particles of rock and metal traveling at high speeds through the solar system, should have gradually contaminated the rings, mixing darker material into the bright ice and dimming their brilliant reflectivity. Scientists calculated that if the rings were truly as old as Saturn, they should be much darker than they appear. The rate of micrometeorite bombardment is relatively well understood from studying the moon's surface, where eons of impact have created a layer of pulverized rock called regolith. Applying similar calculations to Saturn's rings suggested that 4.5 billion years of bombardment should have turned the rings from their current bright white to a dull gray or brown color. Yet when we look at Saturn, we see rings that shine brilliantly, reflecting more than half of the sunlight that strikes them. This observation led some scientists to propose that the rings must have a way of cleaning themselves, perhaps through some process that continually brings fresh, clean ice to the surface while burying contaminated material. However, no convincing mechanism for such continuous cleaning has been identified. The alternative explanation, that the rings are simply much younger than the planet they orbit, began to seem more plausible. The Cassini mission, humanity's most thorough investigation of the Saturn system, provided the evidence that would tip the scales toward a younger age for the rings. During its 13 years in orbit, Cassini made countless observations of the ring's structure, composition, and behavior. But perhaps its most important contribution to the age question came during the mission's final phase, called the grand finale, when the spacecraft made 22 daring passes through the narrow gap between Saturn's atmosphere and the innermost edge of the D-ring. These passes, occurring between April and September of 2017, allowed Cassini to measure the gravitational pull of the rings with unprecedented precision. The strength of this gravitational pull is directly related to the ring's mass. More massive rings would tug more strongly on the spacecraft as it passed nearby. By carefully tracking Cassini's trajectory and measuring the tiny deviations caused by the ring's gravity, scientists could calculate their total mass. The results surprised many researchers. The rings proved to be considerably less massive than many previous estimates had suggested, with a total mass equivalent to only about 40% of Saturn's moon Mimas, or roughly 15 to 20% of Earth's moon. This lower mass had important implications for the ring's age. A lower mass means less material, which in turn suggests a smaller parent body or bodies from which the rings formed. It is easier to imagine a single mid-sized moon being destroyed to create the rings than multiple large moons or a massive primordial disk of material. Furthermore, Cassini made detailed observations of the ring rain phenomenon, the continuous fall of ring material into Saturn's atmosphere along the planet's magnetic field lines. By measuring the rate at which material was being lost, and assuming this rate has been relatively constant over the ring's lifetime, scientists could estimate how long the current ring system could persist before being depleted. The calculations suggested a lifetime of just 1 to 200 million years from the time of formation to complete dispersal. Combined with the evidence from the ring's brightness and purity, these findings pointed to a remarkably specific conclusion. Saturn's rings are likely between 100 million and 400 million years old. To put this in perspective, this means the rings may have formed during Earth's Mesozoic era, the age of dinosaurs. When Tyrannosaurus rex walked the Earth some 68 million years ago, Saturn's rings might have been more extensive and massive than they are today. When the first flowers bloomed on Earth around 130 million years ago, Saturn might have recently acquired its rings, or might have been only a few tens of millions of years away from the catastrophic event that would create them. This realization has profound implications for our understanding of planetary systems. It means that the magnificent rings we see today are temporary, a transient phase in Saturn's long existence. For most of its history, roughly 4 billion years, Saturn likely had no rings, or at most only faint, sparse rings, nothing like the spectacular structures we observe now. And in the future, perhaps 200 million years from now, the rings will be gone, depleted by the ring rain and other processes, leaving Saturn as a simple sphere of gas, bereft of its crown. The implications extend beyond Saturn itself. If rings can form and disappear on timescales of hundreds of millions of years, mere moments in cosmic time, then perhaps other planets in our solar system once had rings that have long since vanished. Perhaps Earth or Mars once wore similar adornments. and throughout the universe, around countless exoplanets orbiting distant stars. Rings may be forming and disappearing all the time, temporary decorations in the endless cosmic dance of gravity and matter. As you rest in this knowledge, imagine the vast sweep of time over which Saturn has existed. Picture the planets spinning in darkness for billions of years, unadorned, until some cosmic accident, an impact, a collision, a close gravitational encounter, shattered a moon and created the glorious rings that now define its appearance. Feel the weight of time, and the strange fortune that we exist precisely during this narrow window when Saturn wears its crown, able to gaze upon a sight that most of the universe's history did not contain, and that the future will not know. When we gaze at images of Saturn captured by telescopes on Earth or by spacecraft visiting the planet, the rings appear as several broad, distinct bands separated by dark gaps. However, this appearance is deceptively simple. In reality, the ring system is vastly more complex, consisting of thousands upon thousands of individual ringlets, each with its own characteristics, separated by gaps ranging from hundreds of kilometers wide to mere meters or even less. The major ring divisions visible from Earth have been given letter designations, assigned not in order from the planet outward, but in the order of their discovery. The C ring, also called the crepe ring due to its darker, more translucent appearance, extends from approximately 74,500 kilometers to 92,000 kilometers from Saturn's center. This ring is less densely populated with particles than the brighter rings beyond it, allowing more light to pass through, giving it a gauzy, delicate appearance. Beyond the C ring lies the B ring, the largest, brightest, and most massive of all Saturn's rings, stretching from 92,000 kilometers to 117,500 kilometers from Saturn's center. The B ring contains the bulk of the ring system's mass. Its particles are so densely packed in some regions that the ring is nearly opaque. Less than 1% of light can pass through the densest parts. The B ring's brightness makes it easily visible even through small telescopes from Earth, and its complex structure reveals itself in stunning detail in close-up images from space probes. The Cassini Division, discovered in 1675 and now known to be approximately 4,800 kilometers wide, separates the B ring from the A ring. For centuries, astronomers thought this division was completely empty, a true gap in the ring system. However, spacecraft observations revealed that the Cassini Division actually contains several faint ringlets of its own, though it remains much less densely populated than the rings on either side of it. The division's existence is largely due to a gravitational resonance with Saturn's moon Mimas. Particles orbiting in the Cassini Division complete exactly 2 orbits for every 1 orbit of Mimas. This 2:1 resonance means that particles in this region receive regular gravitational tugs from Mimas at the same point in their orbit, gradually perturbing them until they move either inward or outward, clearing out the gap. The A ring extends from 122,000 kilometers to approximately 136,800 kilometers from Saturn's center. Like the B ring, it is relatively bright and densely populated with icy particles. Within the A ring lies another gap, the Encke Gap, about 325 kilometers wide, and the narrower Keeler Gap, only about 35 kilometers wide. Each of these gaps is maintained by small moons that orbit within them. Pan in the Encke Gap and Daphnis in the Keeler Gap. These tiny moons, only tens of kilometers in diameter, act as shepherd satellites, their gravity clearing particles from their vicinity and creating waves at the gap edges that propagate outward like ripples on a pond. Beyond the A ring lies the faint F ring, discovered by the Pioneer 11 spacecraft in 1979. This narrow ring, only a few hundred kilometers wide, is one of the most dynamic and puzzling features of the Saturn system. It is actively shaped by 2 shepherd moons, Prometheus and Pandora, which orbit on either side of it. The gravitational influence of these moons confines the F-rings particles and creates intricate structures, kinks, clumps, and braids that change noticeably over periods of just months or years. Cassini observed the F-ring extensively and captured images of these structures forming and evolving, providing unprecedented insights into the dynamic processes that shape planetary rings. Still farther out, we find the faint G ring and the even more tenuous E ring. The E ring is extraordinarily diffuse and extends over an enormous volume of space, from approximately 180,000 kilometers to more than 480,000 kilometers from Saturn's center. Unlike the main rings, which are fed by material from within the ring system itself, the E ring is continuously replenished by ice geysers erupting from Saturn's moon Enceladus. This remarkable moon, only about 500 kilometers in diameter, shoots plumes of water ice and vapor in a space from cracks in its south polar region, called tiger stripes. Some of this material escapes Enceladus's weak gravity and spreads out along the moon's orbit, forming the E ring. The discovery of these geysers by Cassini in 2005 was one of the mission's most significant findings, revealing that Enceladus harbors a liquid water ocean beneath its icy crust, an ocean that might potentially harbor life. The ring system also includes additional components. Interior to the C ring lies the faint D ring, extending down almost to Saturn's cloud tops. Beyond all the previously mentioned structures, there are additional faint rings associated with various small moons. The Phoebe ring, discovered in 2009 using NASA's Spitzer Space Telescope, is enormous and tenuous, extending from approximately 6 million kilometers to 18 million kilometers from Saturn's center, tilted at a different angle from the main rings because it follows the orbit of the moon Phoebe, for which it derives its material. All of these structures, from the dense, bright B ring to the gossamer E ring extending halfway to the orbit of Titan, share certain characteristics. The particles orbit Saturn in accordance with Kepler's laws of planetary motion, with those closer to the planet moving faster than those farther away. This differential rotation creates a shearing motion that helps maintain the ring's extraordinary thinness. Particles moving at different speeds cannot accumulate vertically. Collisions tend to flatten their orbits into a thin plane aligned with Saturn's equator. The rings are also governed by a delicate balance of forces. Gravity tries to pull particles together and down towards Saturn. Orbital motion provides centrifugal force pushing outward. Electromagnetic forces play a role, especially for the smallest particles, which can become electrically charged by solar ultraviolet light and by impact from charged particles in Saturn's magnetosphere. Pressure from sunlight, though extremely weak, can also affect the tiniest particles. All these forces interact in complex ways, creating the intricate structures we observe. As you imagine floating among the rings, picture yourself near a large ice boulder, perhaps 10 meters across, tumbling slowly in space. Around you, countless smaller particles drift and collide in slow motion, their impacts as gentle as snowflakes falling on a winter's day. In the distance, thousands of kilometers away, but still visible as a bright band, more particles stretch in an unbroken line from horizon to horizon, all moving in their silent orbits around the vast golden sphere that dominates the sky, its presence felt in every particle's trajectory, its gravity the conductor of this cosmic symphony. Saturn's rings do not exist in isolation, pristine and unchanging. Rather, they are constantly shaped and reshaped by the gravitational influence of Saturn's many moons, which range from tiny irregular chunks of rock and ice only a few kilometers across to the massive Titan, larger than the planet Mercury and possessing a thick, nitrogen-rich atmosphere that obscures its surface from view in visible light. The relationship between Saturn's moons and its rings is one of the most fascinating aspects of the entire system. revealing the subtle and not-so-subtle ways that gravity can sculpt matter over vast distances and timescales. Some moons orbit within the rings themselves, while others circle far outside the ring system, yet all exert their influence through the invisible but inexorable force of gravity. The most dramatic examples of this gravitational sculpting are the shepherd moons, small satellites that orbit near or within the rings and help to confine ring material through their gravitational influence. The clearest example of this phenomenon occurs at the F ring, that narrow, knotted structure beyond the main rings. Two small moons, Prometheus and Pandora, orbit on either side of the F ring, Prometheus interior to it and Pandora exterior. Each moon's gravity affects the ring particles near it, preventing them from spreading too far inward or outward. The result is a ring that remains confined to a narrow region despite the natural tendency of ring particles to gradually spread out over time through collisions and other interactions. But the shepherd moons do more than simply confine the rings. They create waves and structures within them. As Prometheus orbits Saturn, it periodically approaches closer to and recedes farther from the F ring due to slight differences in orbital shapes and rates. Each time Prometheus comes close to the ring, its gravity pulls on the nearby particles, creating streamers and kinks that trail behind it. Cassini captured remarkable images of these structures, some of which look almost like fingers reaching out from the main body of the ring, created by a single close approach of Prometheus and slowly shearing apart over subsequent orbits as the ring particles move at different speeds. Even more dramatic are the moons that orbit within the rings themselves, plowing through the icy particles like ships through water. Pan, a small moon only about 35 kilometers across at its widest point, orbits within the Encke Gap in the A ring. As it circles Saturn, Pan's gravity clears a path through the ring material, maintaining the gap. But the most remarkable aspect of Pan is its appearance. Cassini images revealed that Pan has an unusual shape, with a prominent equatorial ridge that makes it look remarkably like a flying saucer or a walnut. This ridge is thought to be composed of ring particles that fell onto the moon and accumulated at its equator due to the moon's rotation and the geometry of the ring plane. Similarly, Daphnis, an even smaller moon only about 8 kilometers across, orbits in the Keeler Gap, a narrow division in the outer part of the A ring. Despite its tiny size, Daphnis creates beautiful wave patterns at the edges of the gap, visible in high-resolution Cassini images as ripples propagating both inward and outward from the gap edges. These waves are created by the gravitational pull of Daphnis on the ring material as it passes by, pulling the particles up and down relative to the ring plane, creating vertical undulations that propagate outward and gradually damp down due to collisions between particles. Moons farther from the rings also play important roles in shaping the ring system, primarily through gravitational resonances. A resonance occurs when two orbiting bodies have orbital periods that are related by a simple ratio. For example, one body completing exactly 2 orbits for every 1 orbit of the other body, or 3 orbits for every 2. These resonances are important because they create situations where the two bodies regularly return to the same relative positions, allowing gravitational interactions to accumulate over time rather than averaging out to zero. The Cassini Division, that prominent dark band separating the B and A rings, owes its existence primarily to a 2:1 resonance with Mimas, one of Saturn's larger intermoons. Particles orbiting in the Cassini Division region complete 2 orbits for every 1 orbit of Mimas. This means that a particle in this region regularly encounters Mimas at the same point in its orbit, receiving a gravitational tug in the same direction each time. Over thousands or millions of years, these repeated tugs perturb the particle's orbit, either pushing it inward into the B ring or outward into the A ring, gradually clearing out the division. Similar resonances create many of the smaller gaps and waves within the rings. The Encke Gap is associated with resonances involving Pan and also with resonances from more distant moons. The B ring's inner edge is shaped by a 2:1 resonance with Mimas, while various waves and undulations throughout the rings can be traced to resonances with moons such as Janus, Epimetheus, Prometheus, and Pandora. Some of Saturn's moons may actually be former ring particles themselves, gradually accumulating from the ring material through gentle collisions and gravitational attraction. The small moons within and near the rings, Pan, Daphnis, Atlas, Prometheus, Pandora, and others, may have formed this way, beginning as slightly larger chunks of ice that gradually swept up nearby particles, growing over millions of years into the small worlds we observe today. Their low densities, only slightly greater than water ice, and their irregular shapes suggest they're loosely consolidated piles of ice and rock rather than solid bodies. The largest of Saturn's moons, Titan, orbits much farther from the planet at a distance of about 1.2 million kilometers, well beyond the ring system. Yet even Titan has subtle effects on the rings through gravitational interactions with smaller moons that do orbit near the rings. The entire Saturn system is interconnected through gravity, each body influencing all the others in a complex celestial dance that has continued for billions of years and will continue for billions more, until the rings themselves have faded away. As you contemplate this gravitational ballet, imagine the patience required for these effects to become visible. A moon like Mimas does not clear the Cassini Division in a single orbit, nor in 1,000 orbits, nor even in 1,000,000. Rather, over tens or hundreds of millions of years, countless tiny gravitational tugs accumulate, each one imperceptibly small, but together creating dramatic effects, gaps kilometers wide, waves that propagate through the rings, structures that appear and evolve and disappear over cosmic timescales, all driven by the silent, patient influence of gravity reaching across the void. On July 1st, 2004, after a journey of nearly 7 years covering over 3.5 billion kilometers, the Cassini spacecraft fired its main engine for 96 minutes, slowing itself enough to be captured by Saturn's gravity and become the first spacecraft to enter orbit around the ringed planet. This moment marked the beginning of what would become one of the most successful and scientifically productive planetary missions in the history of space exploration. Cassini was not alone on its journey. Attached to it was the Huygens probe, built by the European Space Agency, designed to land on Saturn's largest moon, Titan. On January 14, 2005, Huygens became the first spacecraft to land in the outer solar system, descending through Titan's thick atmosphere by parachute and transmitting data for more than 90 minutes after landing, revealing a world of methane lakes, river channels carved by liquid methane rain, and a complex organic chemistry that may resemble early Earth before life arose. But while Huygens' mission lasted only a few hours, Cassini would continue operating for nearly 13 years, far exceeding its original 4-year mission timeline. During this extended tenure, the spacecraft completed 294 orbits of Saturn, conducted 162 targeted flybys of moons, and returned more than 450,000 images along with vast quantities of data from its suite of scientific instruments. For the rings, Cassini's arrival brought an unprecedented level of scrutiny and understanding. Previous missions, Pioneer 11 in 1979 and Voyagers 1 and 2 in 1980 and 1981, had conducted flybys, capturing remarkable images but spending only days in close proximity to the Saturn system. Cassini, by contrast, could return to the same features again and again, observing how they changed over time, studying them under different lighting conditions, and examining them with various instruments sensitive to different wavelengths of light and different physical properties. One of Cassini's most important contributions to our understanding of the rings was simply imaging them in unprecedented detail. The spacecraft's cameras could resolve features as small as a few hundred meters across in the main rings, revealing structures that were completely unknown before. The rings proved to be vastly more complex than anyone had imagined, filled with thousands of individual ringlets, each with its own density and structure. The spacecraft discovered propeller-shaped structures in the A ring, created by moonlets too small to be seen directly, but large enough to clear gaps and create characteristic patterns in the surrounding ring material as they orbit. The rings also proved to be more dynamic than expected. Cassini observed the F ring extensively, capturing its evolution over years and revealing just how dramatically this narrow ring can change. Bright clumps appeared and disappeared. The ring's main strands sometimes appeared braided, other times more uniform. Cassini even captured direct evidence of collisions between objects in the F ring, events that created bright streamers of material that slowly dispersed over subsequent months. Cassini's instruments could measure more than just visible light. Its spectrometers examined the composition of the ring particles by analyzing the wavelengths of reflected sunlight and emitted infrared radiation. These measurements confirmed that water ice dominates the ring's composition, but also revealed subtle variations. Some regions of the rings contain more non-icy material than others, appearing slightly redder or darker in color. The spacecraft also detected small amounts of organic compounds called tholins, complex carbon-based molecules created when ultraviolet light from the sun strikes methane and other simple molecules in the presence of water ice. The spacecraft's instruments could also analyze the ring's structure in ways impossible with visible light alone. By passing behind the rings from Earth's perspective and watching how radio signals from Cassini were affected as they passed through the ring material, scientists could measure the density and size distribution of particles with great precision. These radio occultation experiments revealed that the rings contain particles of all sizes, from fine dust grains to house-sized chunks, with the size distribution varying between different rings and even different regions within the same ring. Perhaps most remarkably, Cassini discovered new aspects of how the rings interact with Saturn itself. The spacecraft detected auroral displays in Saturn's upper atmosphere at latitudes corresponding to the edges of the B ring, suggesting that electrical currents flow between the rings and the planet along magnetic field lines. Later observations revealed the ring rain phenomenon, material continuously falling from the rings into Saturn's atmosphere, pulled down along magnetic field lines. This discovery had profound implications for understanding the ring's age and evolution, as described in Chapter 4. As Cassini's mission progressed, its orbit was repeatedly modified to accomplish different scientific objectives. Some orbits took it close to particular moons. Others were designed to study Saturn's polar regions or examine the rings from different angles. But as the spacecraft's fuel supply gradually depleted, mission planners designed a spectacular finale that would maximize the scientific return from the mission's final months. In April 2017, Cassini began a series of 22 orbits called the Grand Finale, during which the spacecraft repeatedly dubbed between Saturn and the innermost edge of its rings. No spacecraft had ever ventured into this region before. It was unknown whether the space there would be relatively empty or filled with dangerous debris shed from the rings. Cassini survived all 22 passes, returning unprecedented data about Saturn's gravity field, magnetic field, and the innermost regions of its ring system. These final orbits revealed that material from the rings was indeed raining into Saturn's atmosphere at a rate much higher than previously thought, about 10,000 kilograms per second, enough to fill an Olympic-sized swimming pool in less than 30 minutes. The spacecraft sampled this ring rain directly, analyzing its composition and finding complex organic molecules alongside the expected water ice, suggesting a rich chemistry in the ring system that scientists are still working to fully understand. On September 15, 2017, having exhausted its fuel supply and to prevent any possibility of contaminating Saturn's potentially habitable moons with Earth microbes, Cassini made its final dive into Saturn's atmosphere, transmitting data about the atmosphere's composition until the very end. The spacecraft burned up in the planet's atmosphere, becoming part of the world it had studied for so long, a fitting end to a mission that had revolutionized our understanding of the ringed planet and its magnificent adornments. As you reflect on Cassini's achievements, imagine the dedication of the hundreds of scientists and engineers who built the spacecraft, planned its observations, and analyzed its data over nearly 3 decades from initial conception to final descent. Picture the spacecraft itself, no larger than a school bus, traveling alone through the vast darkness of space, patiently circling Saturn again and again, its cameras and instruments revealing secrets that had remained hidden for billions of years, waiting only for someone to look closely enough to see them. Although space is often called the silent void, and indeed sound waves cannot propagate through the vacuum between planets, Saturn's rings create a symphony of electromagnetic waves that, when translated into sounds humans can hear, reveal the dynamic and energetic nature of this seemingly serene structure. The rings also display a subtle palette of colors and create various optical phenomena that speak to their complex composition and the physical processes constantly at work within them. Cassini carried an instrument called the Radio and Plasma Wave Science Instrument, or RPWS, designed to detect electromagnetic waves in the radio and plasma frequency ranges. When the spacecraft passed through the plane of Saturn's rings, this instrument detected crackling, popping noises created by tiny ring particles impacting the spacecraft at high relative velocities. Though the particles were often smaller than grains of sand, their speed, typically several kilometers per second, meant that each impact carried significant energy. Engineers had designed Cassini to withstand these impacts, and the acoustic signatures they created provided valuable information about the density and size distribution of particles in different regions of the rings. But the rings create other electromagnetic phenomena as well. Where the rings interact with Saturn's magnetic field, they generate radio emissions. Cassini detected radio waves coming from the regions where the rings cross the planet's equatorial plane, signatures of electrical currents flowing between the rings and Saturn's ionosphere. These currents are driven by the interaction between the electrically charged ring particles and the planet's rotating magnetic field, which drags charged particles along with it as Saturn spins. Scientists at NASA have taken these various electromagnetic waves detected by Cassini and similar data from other sources and converted them into the audio frequency range, creating sounds that represent the radio emissions from the rings and the impacts of particles. The result is an eerie, crackling symphony, pops and hisses that vary in intensity and pitch depending on where the spacecraft was in relation to the rings and what region of the ring system it was passing through. These sounds are not what you would hear if you could float among the rings yourself. There is no air to carry sound waves, but they are authentic translations of real physical phenomena into a form our human senses can appreciate. The rings also display subtle colors that reveal information about their composition and history. To the naked eye, even through a telescope, the rings appear essentially white or very pale golden, the color of relatively pure water ice reflecting sunlight. However, careful analysis of high-resolution images and spectroscopic data reveals variations. Some regions of the rings, particularly in the C ring and Cassini division, appear slightly reddish or tan, indicating the presence of organic compounds called tholins mixed in with the ice. These complex molecules form when ultraviolet light from the sun strikes simpler compounds like methane, ethane, and nitrogen in the presence of water ice, creating long-chain carbon molecules that have a reddish-brown color. The B ring, by contrast, appears somewhat bluer than the other rings, suggesting that its ice is purer and its particles may be younger or have experienced less exposure to contaminants. Some scientists have proposed that the B ring might be continuously refreshed with new, clean ice through processes that are still not fully understood, perhaps involving the grinding of larger particles into smaller ones through collisions. which would expose fresh ice from the interiors of particles. The rings also create beautiful optical phenomena when viewed from different angles and under different lighting conditions. When Saturn's rings are edge-on as seen from Earth, an event that occurs approximately every 15 years as Saturn orbits the Sun and the angle between Earth and the ring plane changes, the rings become nearly invisible, reduced to a thin line, or vanishing entirely for brief periods. This edge-on configuration reveals just how extraordinarily thin the rings are relative to their vast width. When the Sun is on the opposite side of the rings from the viewer, a configuration rarely achieved from Earth but observed by Cassini, the rings display a phenomenon called forward scattering. In this geometry, sunlight passes through the rings, and smaller particles scatter light preferentially in the forward direction. The result is that regions containing more fine dust appear much brighter than they do in normal viewing conditions, revealing structures and faint rings that are nearly invisible when viewed in reflected light. Cassini captured stunning images of the rings in forward scattered light, revealing the gossamer ring extending across a vast region of space, fed by the ice geysers of Enceladus, visible as a faint but distinct glow. The rings also create shadows on Saturn's cloud tops, dark bands that sweep across the planet's surface as it rotates beneath the ring plane. These shadows change their width and position depending on the season. When Saturn is at equinox, the point in its 20.5-year orbit when the Sun is directly above its equator, the ring shadows become mere thin lines. As Saturn moves toward its solstices, the shadows grow wider and shift north or south, creating dramatic contrasts on the planet's pale golden surface. Conversely, Saturn itself casts a shadow on its rings. This shadow is visible in images taken when a spacecraft is positioned to see the rings from the side opposite the Sun. The planet blocks sunlight from reaching the rings immediately behind it, creating a wedge of darkness that moves as Saturn rotates and as the viewing geometry changes. The shadow's appearance depends on the tilt of the rings relative to the Sun and the observer, sometimes appearing as a dark arc, other times as a full wedge extending from the planet's night side. The rings also exhibit what scientists call spokes, transient dark or bright radial features that appear to rotate with the rings, but actually maintain a fixed position relative to Saturn's magnetic field rather than moving at the orbital speed of ring particles. These spokes were first observed by Voyager spacecraft and later studied extensively by Cassini. They appear most commonly around the time of Saturn's equinoxes and seem to be associated with small dust particles that become electrically charged and levitate above the main ring plane due to electromagnetic forces. The spokes typically appear in the B ring and can extend for thousands of kilometers, persisting for a few hours before fading away, only to be replaced by new spokes in other locations. All of these phenomena, the electromagnetic crackling of particle impacts, the subtle color variations revealing chemical composition, the dramatic lighting effects as the rings pass between Saturn and the Sun, the mysterious spokes rotating above the ring plane, combine to create a dynamic, active system far more complex than the peaceful, unchanging band of ice it appears to be from a distance. As you imagine yourself among the rings, picture not just the visual spectacle, but the electromagnetic environment. Charged particles swirling in response to Saturn's magnetic field, radio waves crackling through the vacuum, impacts sending tiny puffs of ice vapor into space where they catch the sunlight before dispersing. The rings are not just a static structure, but a living system, constantly changing and responding to the environment around them, playing their billion-year symphony for anyone willing to listen. Everything in the universe changes over time, and Saturn's magnificent rings are no exception. The same processes that have shaped the rings over millions of years continue today, and they point toward an inevitable conclusion. The rings will not last forever. In fact, by cosmic standards, their remaining lifetime is remarkably short. The ring rain phenomenon, discovered by Cassini during its grand finale orbits, provides the most direct evidence for the rings' eventual disappearance. Scientists measured approximately 10,000 kilograms of ring material falling into Saturn's atmosphere every second, pulled down along the planet's magnetic field lines. This material, composed of water ice mixed with small amounts of organic compounds and rocky material, vaporizes in Saturn's upper atmosphere, adding a component to the planet's chemistry that can be detected through spectroscopy. At this rate of loss, calculations suggest that Saturn's rings will be substantially depleted within 1 to 200 million years, potentially losing enough mass to become much fainter and less impressive than they appear today. Within 300 million years, they may have largely disappeared, reduced to faint, tenuous bands similar to the rings around the other giant planets in our solar system: Jupiter, Uranus, and Neptune, which all possess ring systems, but nothing approaching Saturn's spectacular display. However, ring rain is not the only process depleting the rings. Micrometeorite bombardment also plays a role. When tiny particles of rock or ice traveling through the solar system at high speeds impact ring particles, they can vaporize part of the target, sending some of the material off into space. Over millions of years, this constant bombardment gradually erodes the rings, though at a slower rate than ring rain. Additionally, some of the smallest ring particles can be swept out of the ring system entirely by the pressure of sunlight. Photons from the sun, though they have no mass, carry momentum, and when they strike a small particle, they exert a tiny force pushing it away from the sun. This effect, called radiation pressure, is negligible for large particles, but can be significant for the smallest dust grains. Over time, some of this fine material gradually spirals inward towards Saturn or outward towards space, depleted from the ring system. The gravitational influence of Saturn's moons, which creates the beautiful structures and gaps in the rings, also contributes to their long-term evolution. Gravitational resonances can gradually change the orbits of ring particles, moving them from one region to another or even ejecting them from the ring system entirely if the resonance is particularly strong. The ongoing gravitational dance between the rings and moons is slowly but inevitably reshaping the system. Even collisions between ring particles, which occur constantly as particles orbit at slightly different speeds, contribute to the ring's evolution. Most collisions are gentle, merely causing particles to exchange momentum and gradually flatten their orbits into the ring plane. However, occasionally, collisions are energetic enough to fragment particles into smaller pieces or to knock materials slightly upward or downward, where it may encounter different orbital velocities and be redistributed within the system. Looking forward from our present time, we can imagine the slow transformation of Saturn's appearance over the coming millions of years. At first, the changes would be imperceptible from year to year or even from century to century. The rings would remain bright and impressive for thousands or even millions of years. But gradually, as material continues to rain down on Saturn and as bombardment and other processes take their toll, the rings would become less massive and less opaque. Perhaps 50 million years from now, the rings might appear noticeably fainter than they do today, though still spectacular. 100 million years in the future, they might resemble what we now see when Saturn's rings are at a relatively unfavorable viewing angle, still visible but no longer dominating the planet's appearance. 200 million years hence, they might be reduced to faint bands, barely distinguishable from the darkness of space beyond them. This transformation will occur on a timescale far longer than human civilization has existed. Our entire recorded history spans only about 5,000 years. Modern humans have existed for perhaps 300,000 years. The rings will likely still be impressive when our distant descendants, if we have any, look up at the night sky millions of years in the future. But by the standards of planets and solar systems, which persist for billions of years, the rings are ephemeral, temporary decorations on a world that will long outlive them. Eventually, perhaps 300 million years from now, Saturn will appear as it did for the first 4 billion years of its existence. A simple sphere, pale golden in color, its cloud bands and polar hexagonal storm visible, but no rings adorning its equator. Future astronomers on Earth or elsewhere, if any exist, will have to study old images and data from our era to see what the rings looked like in their glory. They may create simulations based on our measurements, trying to capture something of the beauty that we are fortunate enough to witness in real time. Yet even as Saturn's current rings disappear, the possibility remains that new rings might form. If another moon were to be shattered by collision or tidal forces, a new ring system could be created. The dynamics of the Saturn system continue to evolve, and future catastrophic events could replenish the rings or create entirely new ones. In this sense, Saturn's ring system might be episodic, present for a few 100 million years, then absent for billions of years, then present again when some cosmic accident creates the conditions for their formation. This cyclical possibility raises intriguing questions about the history of ring systems throughout the solar system. Could Earth have once had rings, long since vanished? Might Mars have possessed them during some period in its past? Could any of the other planets have had more impressive rings than they do now? Rings that have since dissipated? We may never know the answers to these questions, but the transient nature of Saturn's rings suggests that they are possible. As you contemplate this distant future, imagine Saturn floating in space, stripped of its glorious adornment, its moons continuing their orbits in the darkness, the space where the rings once reflected sunlight, now empty. But imagine also the billions of years that preceded the rings' formation, when Saturn spun in solitude, and consider the possibility that our present moment, when the rings shine at their brightest, is a special time in the planet's long history, a brief window of cosmic beauty that we are privileged to observe. As we draw this journey through ice and time to its gentle close, it is worth reflecting on what Saturn's rings have meant to humanity and what they continue to teach us about the cosmos we inhabit. These magnificent structures have captured human imagination for centuries, inspiring artists, scientists, and dreamers to look upward and wonder about the nature of the universe beyond our small world. When Galileo first glimpsed Saturn through his telescope in 1610, he could not have imagined what he was seeing. His confusion and wonder at the planet's strange appearance remind us that understanding the cosmos requires not just observation, but interpretation, theory, and the gradual accumulation of knowledge across generations. Each scientist who studied Saturn built upon the work of those who came before, slowly piecing together the true nature of the rings for fragmentary observations and incomplete data. The rings served as natural laboratories for understanding gravitational dynamics long before we could send spacecraft to study them directly. The gaps and divisions in the rings, the way they responded to the moons orbiting nearby, the mathematical relationships that govern their structure, all of these provided insights into how gravity shapes the cosmos at every scale. The same physical principles that explain why the Cassini Division exists also explain why planets orbit the sun, why galaxies rotate, why the universe has the large-scale structure we observe. Saturn's rings are a local, visible example of universal laws, accessible to study in ways that distant galaxies or the early universe can never be. The rings also remind us of the dynamic, ever-changing nature of the cosmos. For much of human history, the heavens were thought to be perfect and eternal, unchanging realms fundamentally different from the Earth, where birth and death, growth and decay were everyday occurrences. Saturn's rings, with their relatively young age and inevitable future disappearance, demonstrate that change is universal. Nothing in the cosmos is truly permanent. Stars are born and die. Galaxies collide and merge. Even structures as iconic as Saturn's rings are temporary phenomena, present for only a brief window in cosmic time. This impermanence lends the rings a kind of poignancy. We are fortunate to live during the narrow window, perhaps only a few 100 million years, when Saturn wears its magnificent crown. For most of the solar system's history, the rings did not exist. In the far future, they will be gone. Our present moment is special, and the images and data we have gathered of the rings preserve them for future generations who may never see them except through our recordings. The exploration of Saturn's rings also demonstrates the power of human curiosity and ingenuity. The Cassini mission, which revolutionized our understanding of the Saturn system, was the product of decades of planning, engineering, and international cooperation. The spacecraft itself was a marvel of technology, packed with sophisticated instruments capable of analyzing the rings in every way our science could devise. The mission required precise navigation across billions of kilometers, delicate orbital maneuvers to avoid hazards while maximizing scientific return, and careful data analysis by hundreds of scientists working together to interpret the flood of information Cassini sent back to Earth. Yet for all our technological achievements, there is still much we do not fully understand about the rings. We do not know with certainty exactly how old they are, only that they are younger than Saturn itself. We are not completely sure whether they formed from a destroyed moon, from a captured comet, or from some other process. We continue to discover new structures and phenomena within the rings, and each answer raises new questions. This ongoing mystery is part of what makes the rings so captivating. They are close enough and bright enough that we can study them in remarkable detail, yet complex enough that they continue to surprise us, revealing new aspects of their nature with each new observation and mission. They remind us that even in our own cosmic neighborhood, within our own solar system, wonders remain to be discovered and understood. The rings also provide perspective on our place in the universe. When we look at Saturn and its rings, we see a system governed by the same physical laws that govern everything else in the cosmos, from the smallest subatomic particles to the largest galactic superclusters. We are part of this same universe, made of the same elements, subject to the same forces. The ice that makes up Saturn's rings is water ice, the same substance that fills our oceans and falls as snow on winter days. The gravitational force that shapes the rings is the same force that keeps us anchored to Earth's surface and guides the moon through its orbit around our planet. Yet we are also unique in a crucial way. We're the part of the universe that has become conscious of itself, capable of studying and appreciating its own nature. We can look at Saturn's rings not just as physical phenomena, but as works of cosmic art, structures of immense beauty created by the interplay of matter and physical law across billions of years. We can feel wonder at their magnificence and poignancy at their impermanence. We can strive to understand them through science, while also simply appreciating them for their beauty. As this narrative comes to its end, imagine one final scene. Saturn floating in the darkness of space, its rings spread wide, catching the light of the distant sun and reflecting it back into the cosmos. Countless billions of ice particles, each following its own orbit, together creating a structure of breathtaking beauty and complexity. Around the planet, moons trace their paths, some shepherding the rings, others bombarding them with water ice to create tenuous outer rings, all moving in accordance with gravitational laws that have governed them for billions of years and will continue long after the current rings have vanished. And somewhere, on a small blue world much closer to the sun, humans look up at the night sky with telescopes and spacecraft, studying these distant wonders, trying to understand how they formed and how they will end, marveling at their beauty and their impermanence, feeling connected to the cosmos through the act of observation and understanding. In this way, Saturn's rings serve as a bridge between the human and the cosmic, between the momentary and the eternal, between the known and the yet-to-be discovered. They remind us that we live in a universe of wonders, that patience and careful observation can reveal secrets hidden for billions of years, and that even the most magnificent structures are temporary, making each moment we have to observe and appreciate them all the more precious. Rest now, and let your imagination drift among the rings, floating in the silence of space, surrounded by glittering ice catching the sunlight, with a vast golden sphere of Saturn below and the stars beyond, eternal witnesses to the billion-year symphony of ice and dust that is playing, and will continue to play until the last particle falls and the rings exist only in memory and in the records we have made of their glory.